Solve a problem? A rigid, well-insulated tank contains 5 kilograms of air at 20 degrees C and 400 kilopascal. A lot of times when you're confronted a problem, you introduce a little illustration, you try to organize the information given. So this is a rigid tank and it's well insulated, and it has a mass of 5 kilograms of air. The initial temperature 20 degrees C, 293 Kelvin, an initial pressure of 400 kilopascal. I anticipate we need the temperature in Kelvin. Why not just get it in Kelvin right away? A paddle wheel stirs the air until the temperature is 120 degrees C. So there's a paddle wheel that comes into the tank. A shaft turns that paddle wheel, spins, and beats the air until the temperature of the air at the final state is now 120 degrees C. So that's 393 Kelvin. The air behaves as an ideal gas at all times. So it's, when I see the ideal gas, what do I think? I think that PV is equal to RT. The ideal gas equation applies. Also, that U is a function of temperature only, and that H is a function of temperature only. 3 things, ideal gas model. The equation, and that the internal energy and the enthalpy are not functions of 2 independent intensive properties, but only one, and only temperature. Ignore the effects of motion and gravity. There's no large macroscopic motion of the air inside. And there's no gravity changes of the air inside the tank during a process. Determine the final pressure. So we're asked to calculate P2. What do you think the units for P2 would be? Kilopascal. Then we were asked to calculate the work transfer. What symbol do you think you want to use for the work transfer during this process from initial state 1 to final state 2? W, units of kilojoule. And then the change in the exergy. Well, because they give us the mass, it's not the change in the lowercase e, but the uppercase E for exergy. So it's going to be E2 minus E1, or delta E. And what are the units on that? Kilojoules. Very good. How are we going to solve for part A? How are we going to find the final pressure? Yeah, for a rigid tank, after you've studied these things for a while, you know the volume of the tank didn't change. And it's not a leaky tank. The amount of air in the tank stayed the same. So the ratio is the same, so the specific volume at the end state is equal to the specific volume at the initial state. I don't have to calculate the V. I just know that V1 is equal to V2. Hence, I can replace the specific volumes using the ideal gas equation by RT over P. RT1 over P1. RT2 over P2. True? So I can get an equation that says the final pressure is equal to the initial pressure times the ratio of temperatures, the final temperature to the initial temperature. And I stick in the numbers. Do I have to put in Kelvin, or can I put in degrees C? I must put in Kelvin because this temperature in this ideal gas equation is absolute, just like this pressure has to be an absolute. And so we calculate the final pressure, P2, to be 536.5 kilopascal. Part B now. What is that work transfer? Okay, apply the first law, which is basically a statement of the conservation of energy. Energy is conserved during the process from initial state to final state. I focus my study on a fixed, clearly defined amount of matter because it's a closed system. That matter is the air. The air. I'm studying the air. change in the internal energy of the air. And we already were told the change in kinetic and potential energy are negligible, so I'm saving a little space by not writing delta KE and delta PE and then striking them to be 0, is equal to how much heat is transferred in during the process from state 1 to state 2. A lot of times I'll put 1 to 2. The book doesn't do that. I like to do it. It's clear to me it's the heat transfer in from state 1 to 2. Likewise, the work out, that's why there's a negative sign, during the process from 1 to 2. Now, we didn't put a 1 to 2 over here. Go ahead and put a 1 to 2, fine. Which one of these three terms is 0? And why? Well, insulated tank, so boom, that's 0. So now if I'm solving for the work, 1 to 2, it's negative delta U, which is negative to the mass, times U final minus U initial, which is negative of the mass. Now I want to calculate the change in the internal energy of air. I know its temperature at 1. I know its temperature at 2. I could go to the air tables. Just ignore the air tables. Just ignore the air tables, okay? Do everything assuming constant specific heat. Can I solve that now using constant specific heat? So what would it be? It would be C sub V times T2 minus T1. When you use constant specific heats, you can get one evaluated at the appropriate temperature, the average temperature. So you say, it started at 20 and it ended at 120. I add those together, I get 140. I divide that by 2, so I want to evaluate C sub V for air at a temperature of around 70 degrees C. Don't bother interpolating. It's not a strong function of temperature. Okay? So in the table for the variable temperature dependent specific heat, they have C sub V for air. Go there and get that value. And it'll be about 0.721 kilojoules per kilogram Kelvin. I'm not accounting for variable specific heat as it changes from 1 to 2. I'm just getting an average value between the two and treating it as a constant over the whole range. Make sense? So do that. Just do that. All right, so when we calculate the work 1 to 2, we find that the work is negative 360.5 kilojoules. Why is there a negative sign? That's right, our thermodynamic first law sign convention is work positive out. Well, it's not positive out, it's actually negative out, which means it's in. The paddle wheel is supplying energy into the air. A work transfer into our system, into the air, by beating it. Okay? What about the change in the exergy? Well, the change in the exergy, E2 minus E1, is equal to the mass times the change in the lowercase exergy, or specific exergy, which can be related as U2 minus U1 plus P naught V2 minus V1 minus T naught S2 minus S1, and we leave off the delta small KE and PE because it's negligible. That equation look familiar? So now I say one of those three terms or groups of terms is 0. Which one is it and why? The V2 is equal to V1, so the delta change in the specific volume is 0. So this term goes away. And it's like, hold it, I already did M times delta U. That's M times C sub V, T2 minus T1. Sure is. That's exactly what it is. And I'm left with calculating this M times T naught times S2 minus S1. Ooh, I have to go back into my recesses, my memory. I need to calculate the change of entropy. Not entropy. The change in entropy for an ideal gas known as air, right? So I can say that S2 minus S1 is equal to either one of two equations is helpful. Either it's C sub P, natural log of T2 over T1, minus R, natural log of P2 over P1, or it's C sub V, natural log of T2 over T1, plus R, natural log of V2 over V1. Both of those equations will work. Both of them will give the exact same answer. Hopefully both of those equations you're familiar with. Both of those equations are available to you on the equation sheet. You don't have to memorize them. It's good to have a good working knowledge of these equations, but you don't have to memorize them. Both of those equations are derived in the previous class. So which one will I use for this problem, because V2 is equal to V1? The second one. Because if V2 is over V1, that's 1, natural log of 1 is 0, and away it goes. It's just a little simpler. 95% of the time, I'll use the first equation. This is one of those 1 out of 5% of the times that I use the second equation. But most of the time, I use the first equation. Okay? So when you do that, you can then calculate that the change in the exergy is equal to, I calculated that the first term is 360.5 kilojoules minus 310.2 kilojoules. So this term right here is 360.5. This term right here is 310.2, but you subtract it. And so we're left with the answer that the change in the exergy of the air is equal to 50.3 kilojoules. All doable? There was 3 parts to this problem, part A, B, and C. 2 parts, A and B, were straight out of Thermo 1. Part C is what's new to Thermo 2. So part A and B were just a review of Thermo 1. For a closed system undergoing a process from initial state 1 to final state 2, we could write an energy balance equation. We could write an energy balance equation known as the first law of thermodynamics, which is a statement that energy is conserved. Could you write it down from memory? I know you have it on an equation sheet, but could you write it down from memory? What would it look like? I want you to do that. Okay, so go ahead and do that for a minute. Write it down. I'll walk around. All right, so the first law, it's an energy balance equation. It's written like this. The change in the total energy is equal to the amount of heat that's transferred in during the process from 1 to 2 minus the amount of work transferred out during the process from 1 to 2. True? Some people can expand this. This is a change in internal plus a change in kinetic plus a change in potential energy if you wanted to expand the change in the total energy. What do you think I have under the blue box right here? Second law. Can we write the second law from memory, which is really a statement of entropy balance? Entropy balance. Can you do that? For what? For a closed system that undergoes a process from initial state 1 to final state 2. Can you please write it down? I'll check a few. So a lot of people wrote down, it's just like the entropy can go up or down in the system, just like energy could increase or decrease in the system. So you say, okay, the entropy can change. So this is S2 minus S1. Okay, so if delta S is positive, just like if delta E is positive, now there's more of it after the process is ended, at the final state. S2 could be greater than S1. S2 could also be less than S1. Just like E2 could be less than E1. All right, but how can it increase? how can the entropy go up with the heat transfer that brings in entropy? So a lot of people wrote an integral del Q divided by TB. True. Some people wrote Q 1 to 2 divided by TB. What's the difference? In the second form, they assume that TB doesn't change. It's constant. The boundary temperature doesn't change. In the first form, they're saying, well, you know, TB, the boundary temperature could go up or down as I'm adding more heat or as the process goes on from initial state 1 to state 2. And we already talked about it. Is there any entropy transfer coming in or out with the work? Does entropy flow with work? No, work is an organized energy transfer, and entropy is a measure of the molecular level disorder of the system. So organized energy transfer doesn't mess up, increase or change or decrease or whatever. It doesn't change the molecular level disorder, the entropy of the system. It doesn't add or subtract entropy from the system. But we could also have that. What was that? There could be entropy production. What is the reason there could be entropy production? Irreversibilities. Now, all that's background for the next blue box that I have covered up. What do you think? What would you guess is the word that's under this black box right here? Right, exergy, balance, equation. True? See the parallelism? Right. Oh, let's go check, see if I'm right. Look at that. Right, an exergy, balance, equation. What do you think the left-hand side of the equal sign would look like? Delta E. But this time we're interpreting E as exergy instead of energy. So the final exergy in the closed system could be greater or less than the initial exergy. True? It's a change in the property exergy, just like a change in the property entropy, just like a change in the property energy. Now, how does exergy go up or down? Yeah, can it be transferred with heat? I think it might. And we'll just put this. Exergy transfer with the heat transfer. And could it be transferred with the work? Yeah. And if we stay with our sign convention, if work transfer is positive out, then that's why we had a negative sign right there. What do you think we need a sign for right there? Positive or negative? Oh, this is a perfect time for our eye clicker question. So what we do is we turn our eye clickers on, and we have our eye clickers on. And now it says welcome. That's nice. It's being kind to me. And I say start a question. So the clock is now running up in that upper corner, 5 seconds and all that. So you hit A for true. A, it needs a positive sign, or B, it's a negative sign right there. So you tell me, I need to put a plus or a minus right here. Hit A if it's plus, positive. Hit B if it's negative. I hit the stop. I then hit the show results. Got it? The results covered up my selection of A and B. A is positive, B is negative. And then the instructor is supposed to push over. Watch this. Right now it says all answers are correct. If I push this button once, it now makes the A green. It says A is correct. If I leave it there, that's the way the instructor says to grade it. If I push it again, it says B is the correct answer. If I push it one more time, guess what it's going to do? The instructor says C is the right answer. Can you tell how it's going like this? And then D, E, and then we're back to where we got, because I can go in a circle not make up my mind. So at this point, there's A selected. At this point, there's B selected. I think we better leave it with B. True? Sure. And so at this point, I hit the get rid of results button. Take away the results, and it's graded. Thank you for participating. And now we just put right here a negative. Do you think we have some sort of term that is complementary with sigma? Do you think we have some exergy destruction, just like we had some entropy production? A lot of times, other books will put S gen right there. They won't use sigma. They'll say, why go to a Greek letter? This book uses sigma. A lot of other books out there used for this type of class use S gen, entropy generation. Here, this book uses E for exergy, D for destruction. You could put DEST for destruction instead of G for GEN for generation. So anyway, what do you think? Look good? So do I need a positive or a negative on this exergy destruction? Answer A or answer B? Let's turn this selection process on. And we are now counting. There's the results. So the instructor would like to say that it's not C, not D, not E, not all of them, not A, but it is B. So we do need a minus sign right there. And now I hit go away from results, and I'm back to continuing the lecture. So why is there a negative sign here? Because it's removing the ability or destroying the ability to do useful work. That's why. So you subtract off that destruction. This equation has more detail. Here it is. You want to derive it? Let me show you how the derivation of the equation. So also, this is the way the book typed it up, because that work here needs to only be the useful work. And there's a little discussion in that. So let's go ahead and derive this equation, knowing this is the type of answer we want. Okay? So we start with the blue system surrounded by the environment. The environment has no heat transfer out with anything else. It has no work transfer out with anything else. There can be an expansion of the system to push back the environment. That's a non-useful work component, because it doesn't help us lift the weight in a gravitational field. It just sort of pushes back the environment. What we really want is that useful work to come outside of the combination of the system and the environment. So what do? We write the first law for the system only. Does this equation look like the first law for the system only? The system undergoes a change in internal kinetic potential energy, as very general. You have the integral of del Q, meaning the accumulation of the heat transfer into the system. How's it going to come into the system? It's only going to come into the system at the expense of from the environment. Right? Okay. Minus the work. Now that work is the useful part plus pushing back the boundary, pushing back the environment. So we write it as a combination of two things. This is P naught. This P naught times V2 minus V1 is, if the system expands, then V2 is greater, and that pushed back the environment, but that's not useful. It's part of the work the system did, but it was not useful. All right, so we put that in here into that work term. What do we do right here? We write the second law for the system only. Does that look like a good second law? Does that look like what we had before? System undergoing? Yeah. And we understand that TB, it's hard to see this subscript B. What does that B represent? The boundary temperature between the two. Okay. And what's sigma? Entropy production. Entropy production. We take the second equation, multiply by T naught, the environment's temperature and subtract that equation from the first law equation, and you get this equation. You then rearrange by grabbing this non-useful boundary work, pushing back the environment over here, and then you just look at that group of terms right here. Guess what? I recognize that. That's the change in the exergy of the system, isn't it? By definition. And then we look at what's left. Okay, this term looks like 1 minus some t, low t, t naught, divided by TB, maybe the high TB. Think of that. And as the system cools down, maybe TB is changing. That's why we need to leave it inside the integral. But if TB is a constant, it comes outside. That the whole parentheses is constant. It's not a function of the amount of heat transfer in or out of the system. But basically, what does this 1 minus T low over T high remind you of? A French guy, Carnot, who did a lot of work in early thermodynamics, and he came up with the Carnot heat engine efficiency, 1 minus T low over T high. That looks like it. So that looks like the percentage of the Q that could actually be converted into useful work. That's the exergy transfer with the work. I'm sorry, did I say work with the heat? It's the exergy transfer with the heat transfer. This is the useful work transfer. Work is our desired form of the energy transfer. So if I have 1 kilojoule of work transfer, that's 1 kilojoule of exergy transfer. It's a 1-to-1. It's 100%. There's no efficiency. It's already in the approved or desired energy form that we want, a work transfer. And then what is this? The exergy destruction. But this exergy destruction is called, it's equal to T naught times sigma, the entropy production. The same cause for the irreversibilities to generate entropy destroys exergy. So some name calling. Here we simplify that equation. It's just, hey, change in exergy is equal to the exergy transfer in with the heat minus the exergy transfer out with the work minus any exergy destruction. Here is the equation. If it's just useful work, if it's just a shaft work, it's 100% that. If you have some boundary work, you have to separate or subtract off that non-useful component. This is the entropy exergy transfer with heat transfer, and this is your exergy destruction. Look good? You ready to revisit the problem we just left? Let's do that. This is the same problem, but now instead of solving for part A, B, C, we have D, E, and F. So now, what is the exergy transfer with the heat transfer for this problem? Remember, it was our rigid, well-insulated tank containing 5 kilograms of air, etc. So I want you to think about part D, answer it on your sheet of paper, and then if you get D, move to E and then F, okay? I'm going to pause. I'm going to come around and see how you do on part D. All right, so the answer for the exergy transfer with the heat is 0. Why? It's well insulated. There's no heat transfer. There's no heat transfer. Q is 0. All right. What is the exergy transfer with the work transfer? Well, we calculated the work transfer before. What was the work? 1 to 2. We calculated it to be negative 360.5 kilojoules. Didn't we? Okay, well, what's the exergy transfer with that work transfer? It's a rotating shaft. It's 100% organized energy transfer. There's no entropy transfer with it. It's 100% exergy transfer. So the exergy transfer with the work is negative 360.5 kilojoules, meaning that it is not out of the air, but actually into the air, negative, but same magnitude as the work. What is the exergy destruction? There's 2 ways to calculate the exergy destruction. Exactly. You can calculate it T naught times sigma, so that you have to first calculate sigma, which is our entropy production, multiply it by the dead state temperature, an absolute Kelvin scale. Or you could do it another way. What's another way to calculate the Exergy destruction? I heard the right word. Who said it? Balance, 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 balance. So you have an equation, it's one of the terms. If I could get all the other terms calculated, then hey, I got it. So what was our Exergy balance equation? It was this. It was the change in the Exergy is equal to Exergy transfer with the heat. Hey, I solved for that. Minus the Exergy transfer with the work. Just solve for that. Oh, I forgot. Is it plus or minus for the Exergy destruction? Minus. It's minus. Because it destroys Exergy. So this was 0 right here. And from part A, or the previous part C, I think it was, the change in the Exergy, it went up 50.3 kilojoules. There was 360.5 kilojoules of work transfer. With it, 100% of that is Exergy transfer. And we have this Exergy destruction. So the Exergy destruction, what does that compute to be? 310.2 kilojoules. Let's interpret this problem a little bit. Think about a bank. Think about money. I go to the bank and I give them $360 input into the bank. Right? That's cash. Later I come back and I say, I'd like my cash back. They say, no problem. There's been a little friction, some irreversibilities. Here's your $50.3 back. Hold it, I gave you $360. I know, but I'm only able to give you $350 back. What happened to the $310? Gobbled up, destroyed. Why? Friction by irreversibilities. Right? And if you go back and look at our system with the paddle wheel, where's our paddle wheel? This is very irreversible, paddling. Now, if you would have put in energy to, let's say, crank up a weight in that system, you know what? You could get 100% theoretically back out if it was a frictionless pulley system. But here, because you're just beating it, oh yeah, you've increased the energy, the work potential for the air to do future work, but not by as much as you put work into it. The next thing we need to do is we need to move to what they call an open system. We do an open system analysis with a control volume. So this is our equation, Exergy rate balance equation for a control volume. It's steady state, so what did they do to the term on the left side of the equal sign? 0. Otherwise, it would be the rate at which the Exergy is accumulating inside the control volume, just like on the energy balance equation, was a rate of energy accumulation inside the control volume. But they said, look, we're not even ever going to have a transient Exergy problem. It's always steady state, so why torture the student with the elaborate equation where that one term on the left is always 0? Let's just put it 0. Simplify life for the student. Equal to, you have, I know it says one heat transfer here, but they did a summation. So guess what? Multiple heat transfers if you have a summation. Get rid of the summation, and what do you got? One heat transfer, and that rate of heat transfer is bringing with it some amount of Exergy. If this is a negative, it's going out of the system, not into the system, and it would be taking it some Exergy. So Exergy flow with heat transfer. And then you have, what is this? Flow of work. It's 100% organized energy transfer. And so it's just like a shaft power out of a turbine. Boom. So that's the shaft power. What about these terms? I know they have one inlet, one outlet. Get rid of the summation. So you have an inlet mass flow rate times a property known as the flow Exergy. It's a lot like enthalpy. But it's the flow exergy. Here's the equation for the flow exergy. H minus H naught minus T naught S minus S naught plus KE and PE. And then this is the mass flow rate exiting times the flow exergy exiting. And then what's this term? Exergy destruction. What you might want to do is right here, can you from memory write down the first law for an open system for a control volume? Can you write down the second law for an open system for control volume? This first law is an energy balance. So we'd have the rate of change of energy in the control volume with respect to time, accumulate or deplete. We have what? Q dot in minus W dot out, right? Plus the mass flow rate in, bringing with it enthalpy, kinetic, and potential energy all in, minus the mass flow rate exit, enthalpy plus kinetic energy plus potential energy exit. Did I leave off any term? Oh, I think we need an energy destruction term. No, we don't have an energy destruction term. Energy is conserved. Entropy is not. Exergy is not. Energy is. So there you go. How about the second law, entropy balance, the rate of change of entropy in the control volume with respect to time? Hey, it can flow in with the heat. 1 over TB. Remember that? Right, right. And then what about the work? Anything with the work? Nothing with the work. It doesn't flow with work. Doesn't. Does it flow with the mass? Mass flow rate in. If I have some inflow of mass, does it bring along some entropy? And is it a lowercase s in? Or is it maybe s in plus ke in plus pe in? No, just this. Why make life harder than it is? Minus the mass flow rate exit, entropy exit. Are we done? Or do we have one more term? We need that entropy production term. I would have preferred this book use S dot gen, but they didn't. What does this book use? Sigma or sigma dot? Which one? Sigma dot, rate of entropy production. All right. Thank you for your attention. We'll pick up there next time.